system performance, under increasing user load, often reaches a critical bottleneck long before server hardware capacity is exhausted. The core dilemma lies in the fundamental latency of data retrieval from primary storage, a problem that direct scaling rarely solves without prohibitive costs. This challenge forces engineers to implement intricate data flow optimizations. Consider a high-traffic web application experiencing intermittent slowdowns. Despite substantial CPU and RAM, database queries consistently introduce unacceptable delays, causing user frustration and service degradation. The system is retrieving the same data repeatedly, an inefficient cycle that wastes computational resources. Caching emerges as the primary mechanism to mitigate this inherent latency. By storing frequently accessed data closer to the point of consumption, caching dramatically reduces response times and offloads the primary data sources. However, implementing an effective caching strategy is not merely about adding a cache. It involves a multi-layered approach with distinct challenges at each level. The first line of defense is client-side caching. Web browsers, for instance, store static assets like images, stylesheets, and JavaScript files based on HTTP headers such as cache control and expires. When a user revisits a page, the browser can serve these assets directly from its local cache, eliminating network requests to the server. This reduces bandwidth consumption and improves perceived page load times for the end user. Moving up the stack, content delivery networks, or CDNs, form a geographically distributed network of proxy servers. CDNs cache static and sometimes dynamic content at edge locations worldwide. When a user requests content, the CDN directs the request to the nearest edge server, which serves the cache data if available. This drastically lowers latency by reducing the physical distance data must travel and offloads the origin server from countless requests. At the application layer, in-memory caches are deployed directly within the application's infrastructure. Tools like Redis or Memcached provide a high-speed key-value store, typically residing in RAM. These caches store the results of expensive computations, frequently queried database records, or session data. By intercepting data requests before they reach the database, application caching significantly reduces database load and accelerates application responses. Beneath the application layer, databases themselves employ sophisticated caching mechanisms. Modern relational databases often include buffer pools for data pages, query caches for SQL result sets, and execution plan caches. These internal caches optimize the performance of data storage and retrieval operations, though their effectiveness can vary significantly with workload patterns and database configuration. The introduction of multiple cache layers, while beneficial for performance, creates a new fundamental problem: cache invalidation. Ensuring data consistency across these distributed caches is complex. If the primary data changes, every cache holding a copy of that data must be updated or invalidated to prevent users from seeing stale information. One common invalidation strategy is time to live, or TTL. Each cached item is assigned a specific expiration time. After this duration, the item is considered stale and is automatically removed from the cache, forcing a fresh retrieval from the primary data source upon the next request. This method is simple but can lead to temporary data staleness or cache misses if data is frequently updated. Eviction policies, such as least recently used, or LRU, and least frequently used, or LFU, address cache capacity limitations. When the cache is full, LRU discards the item that has not been accessed for the longest period, assuming it's less likely to be needed again. LFU evicts the item with the fewest accesses, prioritizing frequently used data. These policies optimize space utilization, but do not directly address data staleness due to external updates. For maintaining consistency with writes, several patterns exist. Write-through caching ensures data is written simultaneously to both the cache and the primary data store. This guarantees data consistency but incurs the latency of writing to both sources for every update. Conversely, write-back caching writes data initially only to the cache. The cache then asynchronously writes the data to the primary store later. This offers superior write performance but introduces a risk. If the cache fails before the data is persisted, the data could be lost. Cache-aside, or lazy loading, places the responsibility of cache management on the application. When data is requested, the application first checks the cache. If a cache miss occurs, the application fetches the data from the database, stores it in the cache, and then returns it. When data is updated, the application writes directly to the database, and then explicitly invalidates the corresponding entry in the cache. Another strategy is read-through caching, where the cache itself acts as a data source. When a request comes, the cache attempts to fulfill it. If the data is not in the cache fetches it from the underlying data store, populates itself, and then returns the data to the application. This simplifies application logic by abstracting the data retrieval mechanism. Despite these strategies, common pitfalls persist. Cache stampede occurs when numerous clients simultaneously request data that is not in the cache, overwhelming the backend database, as they all attempt to fetch and populate the cache. Stale data, as previously mentioned, remains a pervasive issue if invalidation strategies are not robust. Overcaching data that changes frequently or is rarely accessed can lead to increased memory consumption without significant performance benefits. Effective caching and system design is not a single solution but a carefully orchestrated system of layers and strategies. It demands a deep understanding of data access patterns, consistency requirements, and the specific trade-offs each caching technique introduces. The objective is to balance performance gains against the complexities of managing distributed, potentially inconsistent data.